The next speaker is going to be Carolina Giugaite, and she's going to talk about entropy, stochastic gradient descent, optimizes the prior of a valid PAC-Bayes bound. She's a PhD student at the University of Cambridge.
Technical difficulties?
Thank you. So I'll be presenting joint work with Dan Roy. The starting point of this work was the question, how does SGD work? And there is a growing body of work arguing that SGD performs implicit regularization or similarly approximate Bayesian inference. However, the problem with this story is that there are no matching generalization bounds that are non-vacuous when applied to real data and networks the size of the networks used in practice. In this work, we establish non-vacuous generalization bounds for a random perturbation of the SGD solution, exploiting flat minima using PAC-Bayes. So let me tell you a little bit more about flat minima. So you can think about flat minima as a region on the empirical risk surface such that the parameters are insensitive to perturbations. So if you think a parameter lying in a flat minimum, if you perturb it, you will not incur too much additional training error. Whereas on the right-hand side, you see a sharp minima. If you perturb the parameters lying in the sharp minima, your training error will go up a lot. So we take advantage of this flat minima structure using PAC-Bayes theorems to get non-vacuous generalization bounds. So here is the statement one of PAC-Bayes bounds and what it says. So let me just walk you through the math. So for any data distribution D and for any prior randomized classifier P, which we said before seeing the data, with high probability over MID training samples, for any posterior randomized classifier Q, generalization error for Q is bounded in terms of the Kiel divergence. So it just says that the difference between the randomized classifier training error and the true risk is bounded above in terms of the Kiel divergence. So now we can connect this Kiel divergence between our posterior Q and prior P, and we can connect it to flat minima. So you can think about flat minima. In flat minima, you can fit a distribution that's very wide without incurring too much additional training error, which will allow you to overlap with your prior lot, and your Kiel term will be small, giving you a tight generalization bound. And in addition to that, if we're in flat minima and we expand this distribution, we know that it's insensitive to large perturbations, and so our training error will not go up too much. So we'll get a tight bound on the test error. Now, why would one care optimizing PAC-Bayes bounds? So given our training data S, we can find a probably good classifier Q by optimizing the PAC-Bayes bound with respect to posterior Q. For linear type Catoni PAC-Bayes bounds, the optimization problem is of the following form. So we are optimizing over all distributions Q on the parameter space, and our objective looks like the sum of the scaled empirical risk here, and the KL term between your posterior and the prior. Now, it is well known that the optimal choice of the posterior given the prior is called Gibbs posterior, and it's defined in the following equation. So what it says is that for a fixed prior P, our posterior distribution Q has to be absolutely continuous with respect to P, and its density is proportional to exponentiated empirical risk, rescaled empirical risk. So tau is rescaling the empirical risk here. Now we can connect this to Bayesian inference. If we choose the loss to be log loss, and we take that scale parameter tau to be equal to m, then the term minus tau times empirical risk is actually the expected log likelihood under Q, and the objective is V elbow. Also, from the, just as in variational inference, we know that optimizing this objective will, at the supremum, this objective will give you log marginal likelihood. Again, if we choose log loss and tau equals to m. So just as in variational inference, so sampling from Gibbs posteriors is intractable. So we need to, just in variational inference, we need to choose some kind of approximations for Q and P. So in our work, we optimize PAC-Bayes bound by making these approximations. So we choose P to be a scale mixture of Gaussians centered at random initialization W0. We choose a posterior to be also a Gaussian with a diagonal covariance matrix. And our optimization looks like the following. So we are trying to minimize this empirical risk. We have a KL penalty, where the KL is between the posterior Gaussian and our prior Gaussian, scale mixture of Gaussians. And we have this extra term now, which doesn't appear in, let's say, variational inference, which is due to taking P to be a scale mixture of Gaussians and approximating it using a union bound. The KL can be actually computed analytically, and we get this equation just on the bottom of it. So now our optimization looks like having some kind of L2 weight decay towards random initialization W0. S is the posterior variance, and lambda is the prior variance. So we don't want these variances to be too different. So we want the posterior variance not to be too much larger than our prior variance. And this term here suggests that we want the log volume of our posterior to be as large as possible. So we can perform this optimization and tune all the weights and variances of our posterior Q. So now let Q hat be our optimized posterior, Gaussian posterior Q. Now we can approximate the error or the randomized classifier Q hat by using a test set, and we get the number around 3%. So that's kind of the estimate of the true error. If we evaluate our PAC-Bayes bound, we get that the test error is upper bounded by 17% with high probability. So of course there's still a big gap between 3 and 17%, but you might be surprised that actually these are the only non-vacuous bounds in the setting. So of course note that the bounds hold here for randomized perturbation, for perturbation of our SGD solution. Now, so far we've been talking about SGD, but we also know that another question we could ask is SGD actually a good learning algorithm? So there was this recent paper by Zhang et al. Where they show, among other things, that SGD can be trained to zero training error on random label data sets. So if you randomize, let's say, MNIST labels, you can still get zero training error. So SGD will overfit, and the generalization error, of course, will be the worst possible. So maybe SGD is not such a good learning algorithm, and this inspired us to study algorithms that wouldn't overfit by design. So that's why we came across Entropy-SG. Entropy-SG replaces stochastic gradient descent on empirical risk by stochastic gradient ascent applied to the optimization problem. So we are maximizing this F, where F is something called local entropy. And local entropy is supposed to kind of smooth out the empirical risk surface. So whereas you had potentially a lot of sharp, isolated solutions, or minimum, now you smooth out the surface and make it easier for SGD to find flat minima regions. Entropy-SGD was actually designed to have better generalization performance than SGD. Now we can connect Entropy-SGD to PAC-Bayes. So Entropy-SGD is optimizing this local entropy, and you might recognize it as a log partition function of the Gibbs posterior distribution. And I mentioned earlier that Gibbs posterior is actually the optimizing the PAC-Bayes bound. So it's the optimal choice. So what we show in our work is that maximizing local entropy with respect to W corresponds to minimizing PAC-Bayes risk bound with respect to prior's parameters. Now again, from PAC-Bayes theory, we know that we need to choose prior P in advance before seeing the data. So this is not valid. Our bound is now invalid. However, the prior P can depend on the unknown data distribution, and we make use of that by employing differential privacy. So differential privacy, you can think about an algorithm that takes in training data and returns you a randomized classifier, so some kind of distribution over parameters, let's say. And for an algorithm to be differentially private, it means that if you change your input, one input, you want your output distribution not to change too much. So it's kind of the notion of stability or insensitivity to the training data. So we prove a differentially private PAC-Bayes bound, where it's similar to the previous PAC-Bayes bound, but now our prior P can be returned by an epsilon differentially private algorithm. So we can actually optimize our prior using the data in a differentially private way. So now we get a PAC-Bayes, differentially private PAC-Bayes bound where we have this extra term. So our generalization gap is a little looser, and we have this epsilon here, which is the differential privacy parameter. Now, of course, to evaluate this bound, we need an algorithm that would perform this optimization on the prior in a differential private way. And Entropy-SG will not work because it uses SGD, which is not doesn't have enough differential privacy. So we replace SGD with SGLD, stochastic gradient Langevin dynamics, which obtains epsilon delta differential privacy, so approximate differential privacy. SGLD is known to converge weakly to the epsilon differential private exponential mechanism. Our analysis makes a coarse approximation that primacy of SGLD is that of the exponential mechanism. Now we can evaluate the bounds. So we train using Entropy-SGLD, and the bounds we get on the test error now are only 3%, where the true classifier test error is around like 1.5. So it's a lot tighter than what we had before. This, of course, holds with high probability. However, our previous bounds were valid with no assumptions, whereas these bounds are valid under that coarse approximation of SGLD differential privacy, pure differential privacy. And also one thing to note, now, when properly configured to be differentially private, Entropy-SGLD does not overfit on random labels. So in this plot, you see the 0-1 training error varying during training, and we see that it stays around the guessing rate, which is 50%. So we are not overfitting on random labels. Whereas if you had the same plot for Entropy-SGD as original configured, or just vanilla SGD, you would see overfitting very quickly. So our differentially private algorithm does not overfit as expected. So in conclusion, we connect flat minima and generalization using PAC-Bayes bound. We show that Entropy-SGD optimizes the prior in the PAC-Bayes bound, which is not valid, but we use the fact that the prior in the PAC-Bayes bound can be dependent on the data distribution, and we give a differential private version of PAC-Bayes theorem and modify Entropy-SGD so that prior is privately optimized to get the actual bounds. Thank you.
We have time for some questions. I have one question. Could you explain if there is the possibility of these bounds to be used, for example, for hyperparameter tuning, and if you have tried that?
Honestly, I haven't thought about it. So you can potentially, so the way I choose at least differential privacy parameters is because you need to set those before seeing the data. So you usually evaluate and check what kind of generalization gap you could expect given all the other parameters on your neural network. So the size of the neural network, the variances and stuff. differential privacy. So maybe it would be useful in that sense. Yeah, I would need to think about it. Maybe so this is very related, our previous work is very related to variational dropout. So tuning the dropout rate, perhaps it would be useful for that.
Let's thank Carolina again.